This video looks at application questions in arithmetic and geometric sequences and series. So our QCAA subject matter is to use arithmetic sequences in contexts involving discrete linear growth or decay, such as simple interest, and to use geometric sequences in contexts involving geometric growth or decay, including compound interest and annuities. So looking at simple linear growth models to start with, any situation in which a starting amount changes by the same amount over a regular period can be modeled by an arithmetic sequence. So that's why your simple interest is included, because you get that same amount of interest every single year. It doesn't depend on how much is in your account. Very unrealistic, I know, but that's the whole point. So if the values increase at a constant rate, you've got linear growth. If the values decrease at a constant rate, then you have linear decay. So let's look at an example. A new high school starts with 200 students and anticipates increasing in capacity by 150 students each year until the original Year 7 cohort reach Year 12. So I suppose you could make it sound like Calliope High School, for example. So write a formula to model the number of students at the school in terms of numbers of years since the start. So what we've got, we're just modeling it. So if we start with 200, then the next year we're going to add our 150 and we'll have 350. Then we're going to add another 150 and we get 500. And then that keeps going. Okay, so this is year 1, this is year 2, this is year 3, this is our T1, T2, T3. So you should be able to see that it's arithmetic, where T1 is 200 and D is 150. Now it says write a formula to model the number of students at the school in terms of the number of years since start. So T of N equals T1 plus N minus 1 times D. So that's going to be equal to 200 plus N minus 1 times 150, which is 200 plus 150 N minus 150. So just expanded that bracket out. 200 minus 150 is 50. So we've got 150 N plus 50. Okay, so that is the model of what's happening. 150 N plus 50, where N equals the number of years. Since it started. Okay, now the next question says determine the domain for which this linear model is valid. Okay, well, we've got Tn equals 150 N plus 50, and it says the original Year 7 cohort reach Year 12. So you've got Year 7, Year 8, Year 9, Year 10, Year 11, Year 12. It's going to go from N equals 1 up to N equals 6, where N has to be an integer. Okay, that's the only time it's valid. We don't know what's going to happen outside of that. Okay, other way of writing it is 1 is less than and equal to N, which is less than and equal to 6. That's our domain. Simple interest is an example of linear growth because the same amount of interest is added each time to an amount of money. So Sachin deposits $3,500 into a super saver account that pays simple interest at a rate of 5% per annum. Generate the first 6 terms of a sequence that represent the balance of the account from the start. Okay, so we know we're going to start with 3,500 and then we're going to add a certain amount of interest. But how much is the interest? So the interest is equal to 5% of that initial amount. So that 3,500. So that's 0.05 times by 3,500, which is $175. So we are going to add $175 each time. So T1 is going to be 3,500. Our D is 175 because it's arithmetic. So we need the first 6 terms. So 3,500. We add 175 to that. It's 3,675. Add 175, 3,850. Keep going, 4,025, 4,200, and then finish with 4,375. Interpret the value of T5. Well, T5 is equal to 4,200. So it is the principal amount of 3,500 plus 4 years of interest. Where we've got 4 times 175 equals $700. So, and now on the bottom, I've just got the formula for simple interest. I equals PIN, where P is the principal, what you invested or borrowed. I is the amount of interest paid or charged if borrowing, and N is the number of periods for which the interest is paid. Okay. Notice the difference between capital I and little I. Little I is the interest rate for the same time period as N, expressed as a decimal. Capital I is the amount of interest paid or charged if borrowing. Okay, so looking at our question here, our little I is 5%, our capital I is $175. Next, a principal amount of $5,000 is invested in a term deposit at 7% per annum simple interest. The balance of the account at the end of n years is AN. Determine a formula for AN and hence calculate A15. So I'm not going to use simple interest. I'm just going to use my knowledge of arithmetic sequences. So we have 5,000. That's what we started with. And we need to add our interest. Our interest is 7% of 5,000. So 0.07 times by 5,000, which is $350. So it's arithmetic. T1 is 5,000 and D is 350. So Tn equals T1 plus n minus 1 D. So that's going to be 5,000 plus n minus 1 times 350, which is 5,000 plus 350 n minus 350, which is our 350n plus 4650. And it's said formula for AN. So AN is 350n plus 4650. Okay, then it says, hence calculate A15. So A15 is going to be 350 times by 15 plus 4650. Go to your calculator, 350 times by 15 plus 4650 is $9,900. Next, calculate the number of years it will take for the balance to exceed 12,500. So you've got AN equals 350n plus 4650. And we want to know, when is AN going to be greater than 12,500? So 350n plus 4650 needs to be greater than 12,500. We need to get the n on its own, so we need to get rid of that 4650. So we take it from both sides. So we've got 350n is greater than 7850. Divide both sides by 350. And you've got n is greater than 22.43. So it says calculate the number of years it will take for the balance to exceed 12,500. So we want to exceed it, so we're going to round up. Therefore, it will take 23 years to exceed $12,500. Now let's look at compound interest. Consider investing $6,000 at a fixed rate of 7% per annum compound interest over a lengthy period. So after 1 year, it's going to have a value of 6,000 times 1.07. That's our 100% for the original amount plus an extra 7%. So it's 107%. Okay, so after 2 years, we've got that amount, our 6,000 times 1.07, and we need to times all of that by another 1.07. So that's essentially 6,000 times 1.07 squared. After 3 years, we're going to times that 6,000 times 1.07 squared by another 1.07. So you can see this previous amount, and then we're timesing by this 1.07 each time. So what you should be able to see is that formula happening. It's 6,000 times by 1.07 to the n. Okay, where n is the number of years. So and the other thing I hope you're seeing is that we're forming a geometric sequence. We've got 6,000 times by 1.07. Then we times by 1.07 times by 1.07. So that geometric sequence represents compound interest. Our common ratio is our interest rate. So our R is our 1.07. So if P is invested at an interest rate of R% per annum compounded annually, the value of the investment after n years is given by our principal times by our interest rate to the power of n. But note, you don't need to remember the formula. You didn't have to remember the simple interest formula either. Okay, because we can use our knowledge of geometric sequences. But beware. If you're starting out with 6,000 and you're timesing by 1.07 to get your 6420, then you're timesing by 1.07 to get 6869.40. Note, this is T1, T2, T3. This is after 1 year. This is after 2 years. Okay, so when we're using geometric, we're going to have, with our formula, T of 1, or our first term, times by R to the n minus 1. And that's where that n minus 1's coming from. So let's look at an example. Marta invests $2,500 at 7% per annum compounded annually. So it's compounded annually, $2,500 at 7% per annum. So we could use our compound interest formula. which is A equals P 1 plus R to the power of N. Our P is our 2,500, our R is 0.07, and our N is 5. So our A is going to be 2,500, 1 plus 0.07 to the power of 5. Sorry, that equals 2,500, 1.07 to the power of 5, which is approximately 3506.38. Now, if we looked at it as a geometric sequence, so 2,500 goes into our next amount, goes into our next amount, and we times by 1.07 each time. T1, T2, T3. So after 5 years, we actually need T6. So Tn equals T1 R to the n minus 1. That's our formula for geometric. So that's going to be 2,500 times by our 1.07 to the 6 minus 1. Fix it up so you can see it. So 2,500 times 1.07 to the 5. Work that out, you get the same answer. So you don't need to remember your compound interest formula. And the key is to note what's happening with that index. Let's look at the next question. Calculate how long it takes until her investment is worth $10,000. We'd have 10,000 equals 2,500 times 1.07 to the power of n. Divide both sides by 2,500. So we've got 4 equals 1.07 to the power of n, or 0 equals 1.07 to the n minus 4. Haven't done logs yet. So go to calculator, graph y equals 1.07 to the n minus 4, and find the 0 or x-intercept. Okay, meaning that y equals 0. And you will get that n equals 20.5. So we need to round up to 21 because our interest is compounded annually. So we need to round up to the nearest year. So therefore, it will take 21 years. Your other option is to use your geometric, and it would be exactly the same method. Another example, a principal P dollars is invested at 4% per annum compound interest, compounded annually. Use your calculator, so it says use your calculator to determine the minimum number of years for the initial amount to double. So I've got A equals P 1 plus R to the power of n. So our amount is going to be 2 lots of our principal. Our interest rate is 0.04 and our n is, we don't know. So I've got 2p equals p, 1 plus 0.04 to the power of n. Divide both sides by p, not 2. And the p's cancel. So you've got 2 equals 1.04 to the power of n. So 0 equals 1.04 to the n minus 2. You'll then go to your calculator. Graph y equals 1.04 to the n minus 2 and find the x-intercept, because that's when y equals 0. You'll end up getting n equals 17.7. Oh, and note, of course, when you do graph it, it'll actually be y equals 1.04 to the x minus 2. Okay, so you get n as 17.7. It's compounded annually, so we need to round up. So round up to 18. So therefore, it will take 18 years to double. Okay, next, the balance to increase to 5 times the initial amount. Pause the video, have a go yourself. This is that the A equals 5p, the same process though. So 5p equals p 1.04 to the n, divide both sides by p. 5 equals 1.04 to the n, so 0 equals 1.04 to the n minus 5. Sketch, or I should say graph, because you're going to your calculator. Graph y equals 1.04 to the x minus 5 and find the x-intercept. You end up getting that n equals 41, so therefore it will take 41 years for it to increase to 5 times the initial amount. Let's move on. So inflation. Inflation is where money loses its buying power. Okay, but it's no different to compound interest. So no different to compound interest. Concept is the same. So if inflation remains at a fairly constant rate, then you can conclude the expected value of goods and services in future. So an example, if inflation remains constant at 3% per annum, estimate the cost of a $1,500 artwork in 5 years. So A equals P, 1 plus R to the N. Our P is 1,500. Our R is 0.03. And our N is 5. So exactly the same as compound interest. Go to your calculator and it's approximately $1,738.91. So therefore, cost will be approximately $1,738.91. Calculate the present value of an item if it would cost $80,000 in 10 years' time. So our amount now is 80,000. Our P, what it was originally, we have no idea. Our N is 10 and our R is still 0.03. So A equals P, 1 plus R to the N. So 80,000 equals P 1.03 to the power of 10. Divide both sides by 1.03 to the power of 10. So there you go. Our principal is approximately $59,527.50. So therefore, present value is approximately $59,527.50. Let's look at depreciation. That's when things go down. So if an asset has initial value of P dollars and its value depreciates at a rate of R% per annum, the value of the asset after N years, which is determined as D to the base N, is given by, and there is a formula there. But you don't need to remember the formula. Okay, just learn what's going on and apply your knowledge. So a machine bought for $15,000 depreciates at a rate of 12.5% per annum. Calculate the value of the machine after 9 years. So all you have to think about here, it's going down per year. So whereas our formula for compound interest was P1 plus R, we're going to do P1 minus R to the N. It's the only difference. So P is 15,000. Our R is 0.125 because it's 12.5%. And our N is 9. So A is going to be equal to 15,000, 1 minus 0.125 to the power of N. Now you should see what's going on here. You're taking away the percentage from 1. So that means it's decreasing. So this next step is 15,000 times by 0.875 to the 9. So we're decreasing each year because it's times in by 0.875, that 100% minus the 12.5%. So understand why, what's going on. And that ends up equaling $44,509.87. So therefore, machine will be worth $4,509.87. And the next one, calculate how long it takes for the value to drop below 10% of its original cost. So 10% of 15,000 equals 1,500. So we want to know when it's going to drop below that. So A is going to be our 1,500, our P is our 15,000, and our R is 0.125, and we don't know what N is. Okay, so when we set this up, we want our value to be less than 1,500. So we put in that inequality. Divide both sides by 15,000. Let's go 0 is greater than 0.875 to the N minus 0.1. So we're going to graph y equals 0.875 to the N minus 0.1. We're going to find the x-intercept. Okay. Well, to the power of x, not to the power of n. And we end up getting n equals 17.2. So therefore, it will take 18 years to drop below. Okay, we need to round up, otherwise we're not going to be there yet. Let's look at annuities. An annuity is a series of equal payments made annually although any consistent period is allowed, with interest paid annually into the account. So by treating each payment separately, you can use the formula for the sum of a geometric sequence. Okay, so we're using the sum of a geometric sequence to calculate the final value of the investment. Now, the sum of a geometric sequence, if you look at your formula sheet, is S of n equals our initial times by r to the n minus 1 over r minus 1. So that's what we're going to use. So if we look at the example, on Lee's first birthday, her parents open a bank account and deposit $1,000. The annual interest rate is 7%, compounded annually, and added to the end of each 12-month period. So that's where that compounding comes in. The same amount is deposited into this account every birthday. So the same amount is deposited into the account every birthday up to but not including Lee's 21st birthday. So that means they're getting interest, but also the amount is being increased by a deposit. That's why it's an annuity. This is much more real life to what normally happens, okay? And we want the amount after a 21st birthday. So let's think about it. $1,000 deposited on first birthday. Okay, so we're going to have 1,000 times by 1.07 to the power of 20. That's what's in there originally. We're going to have 20 years of interest on that amount because that's not getting withdrawn. So each year that amount is going to be getting interest because it was there right at the beginning. Then when we look at the second birthday, we're going to have 1,000 times by 1.07 to the 19. So that amount is going to earn 19 years of interest. And then we'll keep going until we get to that last payment on her 20th birthday. So for the 20th birthday, we're going to have 1,000 times by 1.07, and we're only going to have that amount. It's not going to get anything more, or you can think about it as being 1. So 1 year of interest. So hopefully what you see is we've got a geometric progression happening, whereas instead of going down this way from 1st to 20th, think about it as going up from this direction. Okay, so you've got your T1 here and we're working up. Okay, so that means our A of 20 is going to equal our 1,000, which is the same every single time. So you can see this 1,000 every time. So we've got that 1,000 times by 1.07 plus 1.07 squared plus 1.07 cubed plus all the way up to 1.07 to the power of 20. So this bit here is geometric. Okay, T of 1 is 1.07 and our R is 1.07. So now we can use that formula. Okay, so we need the sum. Our sum is going to equal our 1,000 times by S of 20. So that's going to be 1,000 times by 1.07, L outside of 1.07 to the power of 20 minus 1, all over 1.07 minus 1. So that ends up being 1,070 times by 1.07 to the 20 minus 1 over 0.07. That ends up approximately $43,865.20. So therefore, there will be approximately $43,865.20 in the account. Now that's much more realistic than with what happens in real life. Okay, when you're investing something, you don't keep taking the amount out, but you keep putting money in. And this is the same with our home loans, where we're dealing with annuities. It's tricky. Go through it, make sure you understand it.